Greetings from the Department of ECE, SJBIT. In the previous session, we have discussed about the RAM, which we are concentrating about the memory cells, which is the first part of module 2. And in this, we have discussed till static memories. So in the static, we have seen about first the basic concepts, then followed by the internal organization of the memory as a array, then SRAM cell, then we have seen about asynchronous SRAM, DRAM cell, advantage of DRAM over SRAM, then followed by asynchronous DRAM cell. So we have here we have seen about an arrangement of 16 megabyte RAM in the form of an array, rows and columns. Rows and columns which are meant for selecting the address. So total 21 address lines have been divided into rows and columns over here to address to address a memory location of 4K cross 512, then data of 8 bits from D0 to D7, and the corresponding rows and address can be selected by using RAS and CAS signals. Asynchronous, as I told you already, it is not all the actions will not happen with respect to the timing diagram. So whereas next in today's session we will be talking about the synchronous DRAM cell. So here almost all the operations means DRAM in the DRAM cell, all the operations is directly synchronized with respect to the clock signal. That's the reason why they named it as a synchronous DRAM. Synchronous with respect to the clock signals. Such memories are called as SDRAM, synchronous DRAM cells. Here itself it indicates. Here itself it indicates the operation which is controlled directly or synchronized with respect to the clock signal. So you will have a sense circuit which are meant for acting as a latch, and you can observe read or write circuits or the latches. There we have seen sense or write circuit. Here it is read or write circuits or latches which are meant for storing, writing the data or reading the data from the cell array. So cell array which has been divided into rows and columns, corresponding row address decoder and column address decoder you need, and row address latch, column address latch obviously you need, and you will have a row address and column address which is selected through this row address and column address selection process. And in this part indicating about data whether you are read operation or write operation. And here you can observe the total cell which is arranged as an array. So during the read operation, the contents in the cell in a row which are loaded into the latches. We are reading the data from the memory. So during a refresh operation, the contents of a cell are refreshed without changing the contents of the latches. If you want to refresh the data, you can refresh it, otherwise not. That is done through this refresh counter, how many refreshes which has been done in which row, which column. So data held in latches which corresponds to the selected columns which are transferred to the output. So for a burst mode of operation, that is transmitting the data at a time, not a single data, too many means a large data if I want to transmit or large data if I want to write, that we call it as a burst mode of operation. Successive columns were selected using the column address counter and clock. So CAS signal which you need not be generated externally. New data, when a new data is placed during a rising edge of the clock signal. So here you have one more controlling unit which we call it as a mode register and timing control unit. As I told, all the operations are controlled with respect to the clock signal, so you need a clock as must. And you have already discussed about RAS and CAS signals, where they are row address select and column address select signals. To select a particular row and column in an array, then they are active low, bar indicating active low signals. That means they will be active when you give signal on that line as 0. Then you have one more timing signal called as read or write bar, whether to read the data or to write the data from the memory. Then CS chip select, which chip that you are choosing. Now you can observe the timing diagram for a burst read of length 4. That means 4 bytes of data if I want to read the 4 bytes or 4 bits of data if I want to read at a time. How in an SDRAM cell it will happen with respect to the clock diagram one can observe. So this is a clock diagram. So first you need to select the address, then you need to do the operation. So as we know, read or write bar operation indicating whether to read or write the data. As it is a read operation, it should be active high. So whenever this is high, line is high, the red data is red from that particular row or column, from that cell. So that cell, how can I select means using this row address select and column address select and address lines. So first you will be sending a row address and row address select signal. So row address will be decoded, then corresponding column address will be selected through column address select signal. Then once if the cell is selected, successive cells data will be read as it is a burst length reading a data of 4. So 4 data will be read. Now we'll observe. First upon sending the row address on the address bus, corresponding row address select signal will be activated. So as it is a active low signal, you can observe, so this has become active low. So now the signal during this period, the row address will be selected during this period. Then you will be sending the column address through the address bus. So corresponding column address select signal, as it is active low, it has become active low. So during that time, row address has become active high. That means already the row address has been selected, and during this period column address has been selected. So row and column, as we got to know, the particular cell has been identified. Now as the cell got identified, I need to do whether read or write operation, which is done through the control signal as read or write. So now you observe this active high signal, as it is active high, so the read operation which has to be performed, and it is a length of 4. So 4 bits of data which is transmitted, which is read from the corresponding cell successively next adjacent to that. So this is how in an SDRAM a burst of 4 bits of length 4 can be read. All the operations which are synchronized with respect to the clock signal. As you can observe, in asynchronous case, it's with respect to the signals, these signals, control signals, whereas all these operations are controlled with respect to the clock signal in case of synchronous DRAM. Coming to this next one, which is about the latency, bandwidth and DDRAM, DDRS in DRAM cell. As we know that after knowing the data, how you will read or write into a memory, one thing you need to know about is latency and the bandwidth. The latency indicating it is a time it takes to transfer a word of data to or from the memory, time it takes. Whereas the bandwidth indicates bandwidth is the number of bits or bytes that can be transferred in 1 second. In 1 second, how many bits or how many bytes that you are transmitting, which is measured as a bandwidth. Whereas latency indicating the time delay, time it takes to transfer a word of data, one word data from between memory and the processor. So in order to increase the bandwidth or to decrease the latency, they have proposed a new technique called as a DD or DDRS DRAMs. DDRS indicating double data rate SDRAMs, synchronous dynamic random access memory cells. So here the cell are arranged in a 2 bank. 2 banks. So twice data rate will be increased. So obviously bandwidth will be increased. So coming to the next one, which is a static RAMs, static memories. It's an arrangement of 2 mega cross 32 memory, which is using a modules of 512K cross 18 bit static memory chips. So all these are chips you can observe. So you have 2-bit decoder with 2 bits. You can have 4 combinations. So 4 cells are arranged in array. So that means each one is about 512K cross 8 static memory chip. Likewise, we have 4 rows with 2-bit decoder. That means total, if I have 21-bit address bus, they will divide that into 2 types, means 2 locations, rows and columns. Here you can observe the first one, A0 to A18, that means total 19-bit address bus, which is used for selecting for 512 19-bit address bus. Then the last 2 bits which are used for selecting a particular chip. So each chip is of size 512K cross 8. 512 means 512 indicating about 9 bits you need. That is a K. 1K indicates about 10, total 19. So 19 bits which is used for selecting one chip, memory chip. Particular memory chip, if likewise you have about 4 cross 4, total about 16. So in order to access that, you need 2 bits to select a particular row or that particular chip, which is done through this 2-bit decoder, the last 2 bits A19 and A20. So here you can observe this is about implementing 2 mega words of 32-bit each. Data size is of 32-bit each. So here they have used 512 cross 8 static memory chips. So first total 32-bit word, no? So that's why 8 bits, next 8 bit, next 8 bit, next 8 bit, likewise. Suppose if I start from this first word, first byte, second byte, third byte and fourth byte. The address means again that's about data. So here you can observe D0 to D7, first byte, second byte, third byte and fourth byte. 4 bytes, about that is about 32 bits. Coming to this 2 mega, which they can address by using this 512. Again they are arranging that as a 4 cross 4. Each column consists of 4 chips, that is each column consists of 4 chips. Each chip is implemented 1 byte of information. The chip is selected by setting its chip value control line to 1. So selecting the chip places the data, the correspondingly read or write operation can be done over here. Main thing is you need to know about how many data lines or how many address lines that you need. Based along with that, whether to arrange the memory as a array, either as a row or as a columns. So coming to this is about a static memory and static DRAM cell, static memories. So similarly you have dynamic memories. So a large dynamic memory system can be implemented using DRAM chips in a similar way as that of static memory chip. Placing large memory system directly on the motherboard, which will occupy usually a large amount of space, and also this arrangement is inflexible since memory systems cannot be expanded very easily. So packaging considerations, they have led to a development of large memory units as SIMMS or DIMMS. SIMMS indicating single inline memory module or dual inline memory module, as we have a space problem, they are dividing that into packaging considerations. They have considered that into DIMM or SIMM modules. All these memory modules are assembly of memory chips on a small board that plugs vertically onto the single socket on a motherboard. Majorly, this occupies the less space and allows easy expansion for replacement of large memory modules. So, we are coming to the next one, which is a memory controller. So, in the dynamic memory chip, to reduce the number of pins, multiplexing address bus which we have made use, that is dividing that into rows and columns. So, they have dividing into two parts, higher order address bus as rows, so which will be latched through a RAS signal, then lower order bus which is used to select the column, then they will be provided later by latching through using a CAS signal. However, the processor uses all the address bits at the same time. In order to achieve that multiplexing, we will be using memory control circuit which is inserted in between the processor and the memory. In between the memory and the processor, we will have a memory controller unit in order to have a multiplexing technology between the processor and the memory, because the memory which is arranged in the form of rows and columns address, but the processor will send the address all the address bits through the address bus at a time. But to access the memory as it is arranged in the form of an array, we have a lower order address and higher order address. So, row and column address which has to be selected. In order to control that operation, we have a separate controller unit called as memory controller unit. So, from processor, the signals which are sent to the memory is addressed through address bus, and control signals like a read or write bar, request operation, which operation is to perform. If it is a synchronous, then clock signal has to be transmitted. Along with that, data bus. Data bus is bidirectional, whereas address bus is unidirectional, from processor to memory, not from memory to processor. Whereas data in between, during the read operation and write operation, you need to process the data in between the processor and the memory. That's why it is bidirectional. So, the controller unit, what it will do, it will select that from address bus, divides that into row and column addresses, and then first it row, if I want to select, then select corresponding control signals like RAS and CAS signals will be sent over. Read or write operation control signal same as that, and along with that one more signal called as chip select, which chip we are using, that to be selected, and clock signal as usual, which is same as the processor clock. So, coming to the next one, which is about a ROM, read only memory. So, SRAM and DRAM, as we have seen, they are volatile, so indicating as soon as the power is turned off, the data in that will be lost. Many applications we need memory devices to retain the content even after the power is turned off. So, for example, when you turn off the when the power is turned off, operating system must be loaded from the disk into the memory every time. So, stores the instructions which would load the OS from the disk. Need to store these instructions so that they will be lost after the power is turned off. We need to store the instructions into a non-volatile memory. So, non-volatile memory is read in the same manner as volatile memory, same process. Separate writing process is needed to place information in this memory. Normal operation involves only for reading of the data. This type of memory is called as a read-only memory. Here you can observe read-only memory, same as your dynamic. Here you will have a capacitor over there, but here you have a latch kind of. So, here you can see the transistor T. Logic value 0 is stored in the transistor, stored if the transistor is connected to the ground point. Otherwise, it will store the data as 1. The bit line, that is bit line. This bit line is connected to the resistor to the power supply. So this is connected through a resistor to the power supply to read the state of the cell word line. If I want to read the state of this, I need to make the word line active. So if this word line is active, then only I can read the data. So that means which will turn on the transistor, the voltage on the bit line. Suppose if this is connected, shorted, then voltage on that bit line will be dropped to 0. If there is no connection to ground, the bit line will remain in high state. So whether when the transistor is turned on, bit line, when it is connected to then you will have, it will store a 0. If it is not connected, then it will store a value as 1. So same, a sense circuit at the end of the bit line is generates the proper value, output value. Data are returned into the RAM when you manufacture. So again in ROM you have different variations. So data written on ROM, when it is in ROM, will be during the manufacturing time, will be writing the data onto the RAM. So later they have made use of PROM, programmable read-only memory. It allows the data to be loaded by the user, not by the manufacturer. So process of inserting a data is irreversible. You can't reverse it. Once if you store the data, it is done. So storing the information specific to the user, if in a RAM, is expensive. Programming capability to a user may be better. So later they have provided with erasable programmable read-only memory. So it is used to store the data when you load the new data. Earlier data will be erased. Flexibility will be provided to the user, erasable and reprogrammable. So it can be done through UV lights. Again you have next type we have is EEPROM, electrically erasable programmable read-only memory. To erase the content, they have to expose to the UV light earlier, physically to be removed from the circuit. Whereas EEPROMs, the contents can be stored and erased easily through electrical signals. So later we have a flash memory, which is having a similar approach as that of EEPROM. It reads the contents of a single cell but writes the content of an entire block of cells. Flash devices have a greater density, higher capacity and low storage cost per bit. Power consumption of the flash memory is very low, making it attractive for use in equipment that is battery driven. So this is a memory hierarchy. One can notice here, you have a processor. In the processor you have a memory in the form of a register and a primary cache memory, L1. L2 both are of cache memory. Primary cache memory, which is there within the processor, secondary cache memory L2 outside the processor. Then below that we have a main memory, then below that we have a magnetic or secondary memory, magnetic disk. So if you look into the size of that memory, it keeps on increases. You have less number of registers and primary cache memory is of less size within the processor because of space constraints. Then as you go on, secondary magnetic memory, which is a hard disk kind of a huge memory which can be used to store the data, large data. So if you look into the speed of the system, speed of the memory system accessing, obviously the processor memory present in the processor can be accessed very easily, at a fast rate. Latency will be very less with respect to these two. As you go on increase with respect to the secondary memory, obviously it increases. So increasing the speed and the cost per bit. As you increase the speed, cost also increases. So fastest access in the data is held in the processor registers, Registers are at the top of the memory hierarchy. Relatively small amount of memory that can be implemented in the processor memory called as a processor cache. We have two levels of cache, L1 which is the processor, L2 in between the main memory and the processor. Next level is a main memory, implemented usually through SIMM. SIMM is single inline memory modules, much larger but it is smaller, slower than the cache memory. Next level is magnetic memory, magnetic disk, huge amount of data that you can store, and it is inexpensive. Speed of the memory is speed of memory access is critical. The idea to bring the instructions and data that will be used in near future as close as to the processor as possible. That's about the memory, main memory. Then cache memory, as already we have seen. We will look into the next topic in the next session. Thank you. Hope you have understood.